This is Professor Coles. We're going through class 14, and this is just the background items I'd like to get through. On resistance design data, we will work some problems in our online class this Tuesday. So this is just an overview of some examples of resistance design data. We'll start with some systematic series, and then I'll give you an example of regression at the end of these slides. Here's an example of a systematic series, and by systematic I mean systematic perturbations of the hull geometry. So you start with some, excuse me, parent form. So here's the parent hull, and these are these lines. This is essentially a front view of the hull, and what these lines are different slices of the hull longitudinally along along the hull, starting from the bow, moving aft, and this is from the mid ship's point, which is the largest section here, and then we have that same section over here, and then moving towards the stern, and this shows what, excuse me, what the transom or stern of the ship looks like. So this gives an idea in 2D of what the three-dimensional actual ship looks like. So you start with some parent hull, and it depends what you want to try to focus your ship series on a particular problem. It might be semi-displacement powerboats, planing powerboats, cargo vessels, naval vessels, and from that parent, then you perturb ideally one parameter at a time. For example, change the prismatic coefficient, holding the other values constant, change the beam to length ratio, holding the other values constant, etc. And you build from that a series of children forms and models for all of those. So the range of number of models, something like 10. I'll show you a series that has 9. I'll show you a series that has 4 dozen models. And that can be used to really assess the influence of different parameters, various parameters, on the performance of the hull. So ideally, use the same length for all the models. That makes the model testing procedure and construction procedure easier, and also for comparison purposes, where you have errors in the resistance coefficients, allows things to be at the same speed, will be at the same Reynolds number because the length is held constant. The turbulence stimulation would be used the same in all the models. You test them over a range of Froude, and that Froude range depends on the target Froude for the vehicle. For the one series I'll show you today, it's around 0.2, 0.3. For the high-speed series, it may be 0.4 to 0.6. And then ideally, you measure important things like what's the tank temperature, the total resistance, of course, from the dynamometer, and other quantities are stored or archived. The data presentation for these systematic series, that really varies very widely. They date to the early 1900s. To modern day systematic series, and the way they stored the data, presented the data, varied over time, as did the nature of how we look at this problem, from going from not really having frictional lines dependent on Reynolds number to modern frictional lines. Early non-dimensional numbers, or they didn't use non-dimensional numbers in the early ship forms. A lot of the coefficients were dimensional, and so you had to be aware that something was in tons and something was in feet, this kind of thing. So you have to be very cautious when you look at the data, the way the data is presented, if you're going to use it in a useful manner. So we're going to look at the Taylor series. These date to the early 1900s. This work was done at the David Taylor Model Basin, and at least the later work, it's a naval facility. And there's a famous paper book, I guess, by Taylor called The Speed and Power of Ships, which would be 1940s, somewhere around there. So we're talking decades of work. This started from a parent form which had a name. Leviathan was the name of it. It was an early British cruiser, I believe. And what the Taylor systematic series present is residuary coefficients. So think about our Froude method of resistance decomposition, subtracting frictional values, leaving you with this residuary coefficient. And that's what the Taylor data presents for you. So it's you're in charge of basically adding friction for your size ship. Remember, with the Froude assumption, this value CR, which include form and wave drag, is the coefficient is constant for any size ship. So you're in charge of putting on the frictional constant. This is probably the most common, I guess, approach, is to give you the residuary coefficient. But you have to be cautious because you have to know how that residuary coefficient was computed. They measured the total resistance and the total resistance coefficient. Then somehow they subtracted friction to result in the residuary drag, and that's what they're giving you. But you need to know the somehow part, because when you go to add friction on, you want to use the same basis that they used for that data, which of course has changed over the years because the way friction is estimated has largely, vastly changed since the early 1900s. The Borowski series, which we'll also use for an in-class problem, they just have a smaller series. I think it's maybe 9 models, and they presented just the total drag on the models. And so your job is to take it like a model test and essentially scale it up to your whatever your full scale ship size is. The BSRA, or British Ship Research Association, I believe that stands for model series, presents in a different way. And essentially, it's a coefficient of what's called a Froude resistance coefficient, where you have effective power here, displacement to the 2/3 power times velocity cubed. They standardize everything to a 400-foot boat, and then essentially you provide tables of correction skin coefficient to adjust that to other lengths. So they're providing essentially a resistance standardized to 400 ship boat, and then what you're doing is modifying the skin friction component to adjust to these other lengths. And so this is a different way of doing this. We probably won't work with the BSRA ship. So the systematic series, this goes back to David Taylor, namesake of the David Taylor model basin, which I mentioned in class when we were talking about ship model testing. This goes back, it is the Leviathan here, I wrote it here. Systematic variations. There's a paper by Gertler, which I put up on the, also the model basin, put up on the website, my course's website. It's a nice report. I'm not sure this, yeah, this would be the right report. Essentially, when Taylor performed one of the systematic series of studies, the water temperature wasn't noted. I don't know if this was because they were not aware of the influence of water temperature and viscosity on, or I should say Reynolds number controlling the skin friction or not. But what Gertler did was went back and reanalyzed the data. They measured the tank temperature as a function of time over the course of a year. And then they just applied that temperature to 40 years prior, correlating the indoor tank temperature with what was really going on in the atmosphere. Then use that to calculate assumed water temperature to get a viscosity, the viscosity to get a Reynolds number, and then use the ATTC 1947 line, which was the current line when Gertler was doing this work in 1954, to recompute the residuary drags, the CRs. So that reports on my courses is very nicely written and really has a nice history going back to the Taylor work and describing what was done, and then Gertler defining quite precisely why the reanalysis was necessary and how it was conducted. So these systematic series had a range of Froude number, 0.9 to 0.6, that's 0.3 to 2.0 in terms of speed to length ratio, in terms of length displacement or slenderness ratio, 5 different ratios of that, 2 ratios at least of the beam to draft ratio. In the paper, it's written as B over H. I think we might see a plot with B over H. The location of the longitudinal location of the center of buoyancy was fixed at amidships. And you had 8 prismatic coefficients ranging with a very wide range, 0.5 almost to 0.86, 80 models in this series. And there were a bunch of other related series in the work that went on the model basin, or that Taylor conducted in the early 1900s, the early decades of the 1900s. So what was reported was this residuary drag coefficient, as always normalized by the dynamic pressure times the velocity squared. And it really allows us to study this influence of different things, speed to length ratio, or you can think of it as Froude number, beam to draft ratio, prismatic coefficient, and displacement length ratio, which essentially is an inverse of length displacement ratio, and to see how when you vary these different parameters, these fundamental coefficients form, what happens to the residuary resistance. It's also useful if you have a ship, you know, you say I want to design a ship, I don't want to pay for the model test, but it's similar to the Taylor series that were conducted, and then you can take your particular vessel with its specific B over T, specific prismatic coefficient, specific slenderness ratio, and get an estimate of the residuary drag as a function of Froude number, put on the friction yourself, and you can get a pretty good assessment of the total resistance coefficient of that bare hull. So the total drag after, I should say, this is post-Gertler, so after the Gertler reanalysis, the total drag coefficient would be his redone residuary drag coefficient plus the line that he was using at the time, which is called the Schoenherr line. It's also called the ATTC 1947 line. So this predated the ITTC 57 line that we've been using. I did present this in one slide in class, and we'll be using this in class to estimate the friction, and if needed, a roughness allowance as well. This shows just one of the many tables that came out of that report. So this is a beam draft ratio. That's written H here, but that's B over T equals 3. Here we have on this axis, this is speed to length ratio, V over root L, where V is in knots and L is in feet. This is sort of the nautical traditional naval architecture version of the Froude number, but it's dimensional, so you have to be cautious about that. It directly corresponds with, can be directly converted, I should say, to the Froude number, which is plotted at the top. So we'll have a look at that because we're more used to looking at that now. So you can see the maximum Froude number in this chart's about 0.3, and the minimum is about 0.15. And what you're seeing here is varying what are called volumetric coefficients. So you have nabla over L cubed. We looked earlier at the slenderness ratio, which is L over nabla to the 1/3. This is also sometimes called the length displacement ratio. It's more common, at least from what I've seen in sort of the sailboat world. They like to use this one. This is pretty much sort of an inverse version of this. So you can directly convert from one to the other. And this is the immersed volume in meters cubed. This is the length of the ship in meters and then cubed. So you have a non-dimensional number either way. You can see as the displacement relative to length increases, you're moving in this direction with these curves. And at a fixed Froude number, for example, here you're about at a Froude number of about 0.238, something like that, or a length displacement ratio of 0.8, you can see what happens is you vary just that parameter, the length displacement ratio, what happens to the residuary resistance in this particular plot. And this is at a fixed prismatic coefficient, a fixed beam to draft ratio. So the only thing varying here is the length displacement ratio. The displacement length ratio, the way they plot it. That's the way they do it here. And these are residuary resistance coefficients times 10 to the minus 3 here. So that's the way we've been plotting it in class. There's a number of these in the Gertler paper. You see a number of these tables. Essentially, that's what it produced. And this required a number of calculations. They had all these ships running all these Froude numbers, and for each of them, they had to subtract out the resistance. In the 40s, when they were doing the reanalysis, they had to subtract out the resistance to get to the residual resistance coefficient, and that was done using a punch card computer was doing all those resistance calculations. So when you punch in your ATTC or your ITTC 57 line in your little desktop, your calculator pull out of your bag, they were doing that with a computer that was installed, a punch card computer at David Taylor Model Basin at that time. I forget what the brand of that was. Our second series is Borowski Systematic Series. It's a smaller series. I think I noted here 9 models. Excuse me. My pen has died, so I'm going to pause this for a second. So you have around 9 models. A midship coefficient of 0.977, And the midship coefficient, I did not introduce to you, but it's very similar to, we talked about CX being the maximum sectional area divided by the beam at the maximum sectional area times the draft at the maximum sectional area. But if you have a ship like this, the midships is the exact halfway point of the boat. So if I have the bow and the stern, halfway is the midship. We take that same section, whatever the section looks like at the midships, we have the area of that section, and you take the area at the midships divided by the beam at the midships divided by the draft at the midships, M is for midships. You have your midships coefficient, which will in practice be quite similar to the maximum sectional area coefficient. And three measures of this beam to draft ratio. You can see there's an overlap considerably with the Taylor. Three ratios of length displacement, or slenderness ratio, and a range of Froude that was fairly narrow, 0.25 to 0.35. But the range, essentially the higher range where the wave drag becomes important, and they needed good assessment of what was going on. They report a total resistance coefficient for these models. So they took the resistance measured in the tank, simply normalized it by the dynamic pressure from the tank and the wetted area of the model to give you the total resistance coefficients, and then you can make a resistance calculation using our Hughes 78 formulation, which we went through in class last week. And again, for CF here, use the standard ITTC 57 line. The reason in the previous one, the Taylor work, we use the ATTC is that's exactly what Taylor used to compute the residuary resistance coefficient. So you need to follow what he did, or Gertler did, actually rather Gertler did, to reconstruct the actual resistance. The best known series for yacht hulls or sailing boats is the Delft systematic series, and this is done in the Netherlands. I wrote 70s to 80s, but this work continues to today. I think there was one particular systematic series that was done at that time, but they're still heavily involved in this kind of stuff. So you're talking about a length to beam ratio, a very large range, a very notable range in the form compared to the prior series. A very wide range of length to beam ratios, extremely wide range of beam to draft ratios, a very wide range, all of these, length to displacement ratio, etc. Prismatic coefficients, midships coefficients, wetted area to displacement ratio, etc. And so they present the data in different form. You can see here a ship in its model rig, testing rig, traveling here, and we'll have a look at the resistance on the next slide. So there's about 50 canoe bodies. When I refer to canoe bodies, I mentioned this in class one time. Yacht hulls tend to have these appendages, use a rudder and a keel, and they're very distinct, in modern racers at least, they're very distinct from the hull itself. And so if you were to remove those, you end up with the hull. So in reality, it would have a keel that would extend down, might even have a bulb at the bottom carrying some mass, and then and a rudder, which you would see behind that. And so this is the canoe body is the hull in absence of those. And the idea is you understand the canoe body, you assume that the interaction between them is small, you understand what's happening in the canoe body, and you can add on additional lift and drag formulations separately for the keel and rudder while the boat's sailing. And so the C here stands for canoe body, or hull without appendages. So they represented a resistance to displacement ratio. So this is a resistance of the boat, so that's a force. This is the displacement of the boat. We sometimes write this delta C, or rho g times the immersed volume, nabla C. And this is residuary, little r. So they've also subtracted off the frictional format. Essentially what you have is a curve fit. You have a constant plus another constant times the location of the center of buoyancy, where's the center of buoyancy relative to the length, plus another constant times the prismatic coefficient, and another constant times this ratio of the displacement, or the volume displacement of the canoe body to the 2/3 power divided by the wetted area, plus another constant times the beam to length ratio. Essentially, it's a curve fit. And going on and on. Up to 8 terms that you have here. I think there's some additional terms, but 8 terms written here. So it's a function of these forms, so it's a curve fit through those forms. And if you come in and say, okay, I've designed a particular sailboat, and you dump the geometry of that sailboat, and you designed it in whatever program you designed it in, and from that you have these coefficients of form for your particular boat, being the length ratio, prismatic coefficient, location of the center of buoyancy, etc. You can put it in this curve fit and come up with what your residuary coefficient is going to be. So it's kind of mapping as a table associated with it. So you have these coefficients A0 through A8, and this is Froude number in this direction here. So if you say, okay, I'm at a Froude number of 0.4, you grab these coefficients and you come back here to this polynomial and you pop them into this polynomial, and you have an estimate of your non-dimensional resistance here, RR over displacement. They also have for their systematic series a wetted area estimate. So if you know your coefficients of form, your midships coefficient, your displacement of volume displacement of the canoe body times the length of the boat, and the beam to draft ratio, you can get an estimate of you get the wetted area that they used in their forms, and this can be used to calculate the skin friction of the boat. This shows just an example of the Delft Systematic Yacht series. These are the 3 parent hulls, which were hull 1, 25, and 44 in their numbering system. And you can see as they vary the Froude number here, and again you can see the rise and drag that's occurring here between 0.4 and 0.45. The drag starts to increase rapidly, and this is actual resistance in newtons of their 10-meter hulls. And they have obviously very different characteristics, these parents of these 3 series, because the resistance are drastically different at the same Froude number over the same length. So these are going to be a lot beamier boats with much higher prismatic coefficient than, say, these boats down here that have a much larger, much lower beam and smaller length displacement ratio. There are other series. I did mention this BSRA series, the British Ship Research Association. The Series 60 was a famous series. I think also a study, the David Taylor Model Basin, of single screw merchant ships. And that's a series that's commonly used for CFD skill assessments, because they did a lot of data, not just resistance data. They made other measurements. Over the years, they've made other measurements around the hull to make sure your CFD calculations are producing the right wave field, the right wake, etc. Then some high-speed series. You had a round bilge, meaning that the sectional form is rounder, like this. Semi-displacement, so now you're getting into Froude numbers above 0.4, and so there's some planing going on. And then actual planing boats, where the boats are going fast enough that they produce lift, and it reduces the effective displacement of the hull. This is an example of this. When I say hard chine, you can see that the section of the boat takes a corner, and this little corner here is referred to as a chine. This indicates that the boat's been designed for planing. So this, again, these are all 3 of these series were done at David Taylor Model Basin. I think this was in the high-speed tank, this last 62 series. Delft Yacht series I mentioned, and there's a number of other ones. What some people have done, and I'll show you just maybe the most well-known of this, is perform regressions. And what they've essentially done is taken these series and other data and thrown them into a statistical analysis to analyze the residuary coefficient as a function of all these different important non-dimensional coefficients of form of the boat, as well as Froude number, which is a measure of the speed, a non-dimensional measure of the speed. And they've run a regression, and regressions essentially you feed it this data and build this model that maps those coefficients of form to the residuary coefficient in a statistical sense. And you can do that by sort of these multi-regressions by adding variables in, making sure that you're accounting for correlation between your variables, which can be challenging. If you have a lot of variables feeding the system and they're all independent, That can be challenging if you don't have enough data. And so some of the tests can be, you can test it by saying, okay, if I remove one of these variables like CB from my regression, then it gets worse. Or if I add a new variable in and say, oh, I should have thought about this particular coefficient of form, and you put it in your regression and it doesn't improve, then you know that you've built a good regression. You can test them by building the regression using a lot of data, but you don't put all the data in. You keep a few data points aside, and then later on you go check and you say, how well does the regression do on this known data? And that's a measure of residuals or skill assessment that can be done. Maybe the best known, at least that I've seen, is Holtrop and Menon. I put the paper up on my courses. It's a very easy read. As you go through it, you'll just see all the things we talk about in class all the time. And it's a nice little calculation that shows how essentially you can estimate the total resistance of really any ship, and it's sort of applicable to this kind of range of ship. This is the data that fed this regression is across these kind of things. So if you came in out of left field and said, okay, I have a sailboat, which might have super high beam to draft ratio that wasn't in the data that fed this, it probably is not going to give you a very accurate answer. And so, but if your vessel of interest is in this kind of range, then you can get a good assessment. And it certainly is a great starting point because it's extremely inexpensive compared to a model test or CFD to run this regression. And so what the regression gives you is two things, essentially. One is you're reconstructing the total resistance using your ITTC57 formulation, which requires the form factor and the wave drag coefficient, RW, or wave drag, RW, and some extra resistance. So this could be air resistance, appendages, etc. And so what Holtrop and Menon gives you at a minimum is K, the form factor, is a function of stuff, of these coefficients of form. And it gives you the wave drag as a function of stuff as well. And so the stuff, the coefficients of form influence the values of these coefficients, C1 and C2 and C5. They're particular numbers. If you look at the Holtrop and Menon paper, you'll see C1 equals this thing, and it's some function of coefficient of form, C2, etc., C5. And then you have here is your Froude number dependence for influencing your wave drag. And so the paper describes how these calculations work. I have a MATLAB code that essentially mimics this calculation. The homework problem for the undergraduates, if undergraduates that don't have access to MATLAB, which is totally understandable in this situation, just write, as I mentioned, as you'll see in the homework, it just says write no access to MATLAB and you'll get full credit for it. But that MATLAB code basically just does this calculation. So you're asked to throw in some coefficients of form and a speed and get an assessment of what the resistance of the ship is. So let me end it there. We're going to, in class, work two problems. We're going to do, if I remember correctly, we're going to use the Taylor systematic series to do an estimate of a Liberty ship, I think, and we're going to use the Borowski systematic series to get an estimate of the effective power of something else. I think it's a twin screw destroyer, something like that. So we're going to do that in class on Tuesday.